starting with our topic, work, energy, and power, right? So when we are going to, of course, start by talking about what is work, right? So what do you remember about work done? You have covered it before, you know what is work done. So what do you remember about what is work done?
Force into distance.
Yeah, force into distance in the same direction as the force, right? That it is very important that you always specify what distance you're talking about, because the formula, for example, for your turning effective moment is also force into distance, right? That is also considered to be force into distance. So in this situation over there, when you talk about turning effective moment, you are taking perpendicular distance. In this situation, you're going to be taking distance that is going to be in direction of the motion, right? So that is what your work done actually is. Now, when we are going to talk about it, so work done, the formula for it is the same, and it is of course going to be force into your parallel distance or distance in the direction of the force. So the formula is going to be force multiplied by distance, and the unit for work done is of course basically going to be in your joules, right? Now, when we are basically going to talk about our topic of work done, so in this situation, the way it gets, they give you questions in your situation over here, in your exams, is that they ask you to calculate work done at an angle, right? So they're going to actually give you a situation where you will be on a slope, or where you are going to be present on some kind of, angled surface, and then they will ask you, now calculate what is the work done, what is going to be your work done. So in those situations, you are then going to have to decide, take your force and divide it into a vertical component and divide it into a horizontal component. And then you will have to then calculate what the work done is. So the formula for work done is the same as before, as what you have done before as well. The difference comes in work done when basically your work done is going to when you talk about work done, they will give it to you at an angle surface. So in those situations, you will have to go ahead and you will have to resolve the vertical component and the horizontal component of the force, so you can actually calculate what the work done is. Now, work done is equal to energy transferred, right? Work done is equal to energy transferred. So if energy transferred is given to you, you can also use that to do the calculations for work done. Now, when we talk about basically your situation, right? So let's go ahead and take an example. We will take an example where, let's say you have a box and this box is being pulled up at an angle. Okay. The box, this angle is around 30 degrees, and the box is moving a distance of, let's say, 5 meters. And the value of force is 200 newtons. Now, if I ask you to calculate work done in this situation, you will have to go ahead and divide it into your vertical component and into your horizontal component. And in this situation, what you will have to go ahead and do, you will have to go ahead and of course then do your calculations. So in this situation, you need to find the horizontal component. Why not the vertical component? Why the horizontal component? Because we always take force in the same direction as the distance. So if I'm covering horizontal distance, I will take horizontal component of the force. So to solve this, I will have to do 200 cos 30, and then I will multiply that by 5. So I will do force into distance, and for force, I will take 200 cos 30. And that is how I'm going to basically go ahead and do my calculation. So that is one thing that you are going to always have to remember. Now, that is one thing, that is your work done. Moving out from our work done, we also have to go ahead and take a look at our energy. When we talk about energy, we know we have gravitational potential energy. The formula for gravitational potential energy is the same, mgh, right? Which is going to be mass into gravitational field strength multiplied by your height. Exactly. And when we are going to talk about it, uh, your gravitational potential energy. What exactly is gravitational potential energy? When I am lifting an object, I am doing work, right? Whenever I'm lifting an object, I'm doing work, so I can raise that object against the gravitational force. I am working against the gravitational force. I'm putting in energy, right? I'm using my body's energy to actually work against gravity and lift up that object. Now I am doing work against that gravity when I am lifting up an object. So that work done, the work done by my body is being turned into gravitational potential energy. The energy from my body is being stored inside the object as gravitational potential energy. That is why there is gravitational potential energy. That is why it's related to height, because to lift the object up, you have to do work done. That work done is stored inside the object as potential energy, gravitational potential energy. Potential energy means storage energy. All right. So whenever you're doing work against any force and your energy is getting stored in the object, that is potential energy, right? So gravitational potential energy is when I'm doing work against gravity, and that energy is stored inside the box. So my chemical energy, the chemical energy of my body, because of course my body is producing ATP and all that, you've done biology. So the chemical energy of my body is being turned into gravitational potential energy. And for example, if I decide to leave the box, if I decide to drop the box, that storage energy will turn into kinetic energy. So energy cannot be made, it cannot be destroyed, it can only be transformed from one form to another. So that is what your gravitational potential energy is. When we talk about potential energy, there can be different forms of potential energy, right? For example, elastic potential energy. You will do elastic potential energy later on. When you're going to do your deformation of solids, you are going to study about elastic potential energy as well. So when I am stretching a spring, when I'm pulling the spring apart, I'm doing work against the elastic force, against the elastic recoil of the spring. I'm putting in work. When I am putting in work against the elastic recoil, that gets stored inside the spring as elastic potential energy. Just like that, we have electric potential energy, which you will study when you do your A levels, right? Electric potential energy is basically, for example, if there are a positive charge and a negative charge, right? They both are experiencing a force of attraction. If I try to move them away from each other, I am working against that attraction, right? I'm pulling them away against the attraction. So the energy is the work I am doing to pull the two opposite charges away. That work that I'm doing will get stored inside them as electric potential energy. So potential energy can be of different types. And the name of the terminology is going to again depend upon what you're working against. So if you're working against gravity, it's gravitational potential energy. If you work against electrical force, it's electrical potential energy. If you're working against elastic force, it is elastic potential energy. So that is what gravitational potential energy actually is.
So we
Now,
have
yeah.
related to electrical energy, yeah?
Yeah, you will do that, but not this year. You're going to do that next year.
This year, yeah.
You will do elastic potential energy this year.
Okay.
Elastic potential energy is in the deformation of solids topic. So you'll cover it when you do that.
Okay.
Okay, then of course we have our kinetic energy, right? So when we talk about kinetic energy is half mv square. We already know that it's half mv square. Right now, how do we get the equation? How we derive the equation half mv square? The derivation of the equation is pretty simple. We are actually taking an equation v square is equals to u square plus 2as. Now, we are assuming that the object is being accelerated from rest, which means that the initial velocity will be 0. So v square is equals to 2as because initial speed is 0. Now, we will bring this 2 over here in the denominator. So it will become half v square is equals to as. Now, when we talk about our acceleration, so our acceleration can be replaced by another terminology, right? It can be replaced by another possible term. And when we're going to talk about it, the other term that we can go ahead and replace it with is F is equals to ma. So that means acceleration is equals to force upon mass. Okay, so I can write down half v square is equal to force upon mass multiplied by distance. Mass will go here in the denominator. It will become half mv square is equals to fs. Force multiplied by distance is equal to work done, right? Work done is force multiplied by distance. So it will become half mv square is equal to work done. And since work done is equal to energy transferred, so half mv square is equal to our kinetic energy, right? So that is how we actually derived, and that is how we got the equation for kinetic energy. We went ahead and we used the formula of our kinematic equations. Okay, so when we talk about our entire topic of our energy, we know that the principle of conservation of energy states that energy cannot be created and energy cannot be destroyed. It can only be changed from one form to another. So often in situations when you're going to talk about it, you're going to go ahead and you're going to remember this particular concept. You're going to go ahead and always remember this particular concept that energy is being transformed. It's going to allow your calculations to be really easy. Just give me one. Okay. So what is going to happen is that yeah, you're going to go ahead and you're going to always remember your energy transformation, right? So you always remember that energy is being transformed from one to form to another, and that is what is going to allow it easy for you. It's going to make it easy for you to solve your calculations, right? You're doing your questions. So for example, let's go ahead and take a situation where they have given you, let's say, a simple pendulum. You're not going to be dealing with a lot of questions related to pendulum because they come under harmonic motion, which is once again A levels and not AS. But still, let's say you have a ball that is swinging on a pendulum, and that ball is basically going in this particular direction. So you know when the ball is at the maximum amplitude, the velocity is going to be 0. And when the ball is going to be passing the very center, the velocity is going to be maximum, right? That is what, if you remember from your IG level, that is what we had studied. That when the ball is at a maximum amplitude, a pendulum is at a maximum amplitude, the velocity is 0 and the ball will have maximum velocity when it is basically passing through the center. So when the ball is going to be at maximum amplitude, it is going to have what? It's going to have gravitational potential energy. And as the sphere is going to fall, so it's basically falling, right? So as the sphere is going to fall, it's going to come towards the center, gravitational potential energy is going to turn into kinetic energy. And once again, as the ball passes through the center field, the ball will continue rising and your gravitational potential energy, your kinetic energy will again decrease and turn into gravitational potential energy. So we always need to remember whenever we're doing calculations, we always need to remember that that our energy is being transformed from one form to another, right? So for example, they say a pendulum consists of a brass sphere of mass 5 kg. So the mass of the sphere is 5 kg. And the sphere is pulled to the side so that it is 0.15 meters from its lowest position. So this is the lowest position over here. And the ball is 0.5 meters above it. So the height of the ball above the lowest position, this is the lowest position, the height of the ball above the lowest position is 0.15 meter. It is then released. How fast will it be moving when it will pass through the lowest point? So what will be the speed over here? At the lowest point, at the central point, when the velocity is maximum, what will be the speed of the ball? That is what you basically have to go ahead and calculate. So when you're going to go ahead and take a look into it, now how can you do that? You remember the fact that over here, the ball will have gravitational potential energy. And that gravitational potential energy will turn into kinetic energy. So you start by first calculating gravitational potential energy. What will be the decrease in gravitational potential energy? So you go ahead and do mgh. Mass is 5 kgs, G is 9.81, and H is 0.15. You do that and you calculate the decrease in gravitational potential energy. The decrease in gravitational potential energy is going to be equal to the increase in kinetic energy. So whatever answer you get, you will write down is equals to half mv square and you will solve for velocity. So that is one thing you're going to have to go ahead and always remember, how your energy is being transformed and it is being conserved. And we will take more look, we will talk about this more, or you will actually, when we do the questions, you will take a look into how this actually can help. Now, another thing is that we can use this concept that gravitational potential energy is going to turn into kinetic energy. So change in our gravitational potential energy is equal to our gravitational potential energy is equals to change in kinetic energy, right? So when we are going to talk about it, we actually, we can use this concept to find another formula, right? So basically your mgh is equals to half mv square. The mass and mass can be cancelled out. So we are left with gh is equals to half v square. This 2 will come in the numerator. 2gh is equals to v square. And you will apply an under rule to cancel out the square. So you end up with another formula, and that is velocity is equals to 2gh. So by using this concept, we can find another equation, that is velocity is equals to 2gh. Now, when we are going to talk about it, another thing we need to talk about is efficiency, right? What is efficiency? Efficiency, basically the formula for efficiency that we need to go ahead and know about is that efficiency is useful energy output divided by total energy input multiplied by 100. This can be power as well. Useful power output divided by total power input. Useful energy output divided by total energy input. Useful, you can also use work done. right? So when you're going to go ahead and turn it your useful output divided by total input multiplied by 100, that will basically give you your efficiency. When we talk about the term useful, so your energy is always being transformed from one form into another. Take the example of our car, right? So in car, you're taking chemical energy, you're taking a combustion reaction, and you're using it to produce kinetic energy that will allow the car to move. So the your chemical energy turning into kinetic energy is useful energy output. That is what we want. But as we know, that is not all that happens. Along some of the chemical energies turn into kinetic energy. Other than that, other forms are also done. Some of it also goes ahead and turns into heat energy, or some of it also goes ahead and turns into other forms of energy, sound energy, right? So these, if will be considered wasted forms of energy, because we want it to turn into kinetic energy. So the kinetic energy output is what we will consider. So we always want the useful output, the output that we actually want, right? So that is about efficiency. Then we have power. What is the formula for power? Power is equals to work done upon time or energy upon time. Right? The unit of power is watt, which you already know about from your IG. And now we can use this entire concept to come up with another formula for power. So power is equals to work done upon time, right? So power is equals to work done upon time. Now, work done is equals to force multiplied by distance. So I can go ahead and write down power is equals to force multiplied by distance divided by time. Now,
Miss, in the exam, we'll
yeah,
have to do all of these derivations. Like in questions, we'll have to do all of these derivations and find out which formula.
unless, no. So I'll tell you what. Sometimes they give you a question where they say, show us how you derive the equation. Only in those questions will you have to show the derivation. If it's just a normal question of solving it, then you just solve it directly. That's it. Unless this, yeah.
The solving questions, there can be times where we'll have to like apply this, like the things you taught me.
You can just learn the final formula. You don't, for example, this one, velocity is equals to 2gh. You don't have to use the derivation when you're doing calculation. You just remember velocity 2gh and use it directly. The derivation is first of all there for you to make your concept and understand where we're getting the equation from. And secondly, the derivation is, they do give questions where they say derive the equation. So in those equations, will have to do your derivation, or derivation is generally just for you to understand how we are getting those particular equations, right? And but if you're solving numerical questions, simple calculations, you don't have to worry about any of that. You just go ahead and simply apply the formula, the final formula, derived formula. That's it.
Okay, Miss,
Okay. So you can say power is equals to force multiplied by distance. So power is equals to work done upon time. Work done can be replaced by force into distance. And we know distance upon time is equal to velocity. So I can write down power is equals to force multiplied by velocity. That is another formula for power. So power is equals to work done upon time. Power is equals to energy upon time. Power is equals to force into velocity. So these are basically the formulas that you have. So that is just the theory portion of what we have to relate in relation to our topic of work, energy, and power. And is there any confusion so far? Do you want to ask anything related to what we covered?
No, Miss, everything's clear.
Okay, all right. Then let's go ahead and actually take a look at our past papers and see how the questions are given and how you're going to actually solve it, right? 1 second. Okay. A car, this is what I meant. They'll ask you on a slope. A car starts from rest and travels upwards along the straight road, inclined at an angle of 5 degrees to the horizontal. The length of the road is 450 meters and the car has a mass of 800 kilograms. The speed of the car increases at a constant rate and is 28 meters per second at the slope. Okay, the first part of the question is related to kinematics, and then we have to talk about energy. So let's go ahead and start solving it. Determine for this car traveling up the slope its acceleration. So you have to calculate the acceleration for the car traveling up the slope.
Um,
This is all the information that you have.
This is it 0.871.
Just give me 1 second. I'm not doing my calculation.
Okay.
So what answer are you getting?
I got 0.871.
Good job. It will be 0.87. You simply have to do I did v square is equals to u square plus 2as, right? Initial velocity will be 0 and you'll just do your calculations. For the next part, the time taken to travel the length of the slope. What will be the time taken to travel the length of the slope?
Okay, we can find that. Miss, will it be 32.14 seconds?
Just give me 1 second.
Okay.
Sorry, my calculator is just, I'm using my phone, so the calculations are slow. Right, so what answer are you getting?
32.14 seconds.
Yeah, that's fine. Okay, that is correct. Now the next one is the gain in kinetic energy. What will be the gain in kinetic energy?
Okay, let's go to 31,003. Okay, no. 313600.
Yeah. Can you turn it into standard form and tell me?
Yeah, okay, 1 second. 3.1 into 10 to the power 5.
Yeah, that's fine. Now you have to calculate the gravitational potential energy.
Yes, can we take displacement as our height?
You can't take displacement as your height. You need vertical height. You have to calculate vertical height.
Okay.
You will have to find out what the vertical height is. You cannot use this displacement to get your answer. No. You will always remember that gravitational potential energy is always the vertical height, always.
So can we like find this?
You have to calculate this. The one that I've made the arrow. Hold on, let me show you. Look, I'll just draw it in another color.
Okay.
This is the height you have to calculate. The one I made in maroon, this is what you have to calculate. You'll have to find this height and use this height. It always has to be vertical height, always, whenever you're talking about MGH.
Okay, so miss, we can do this here. This is going to be 90. This is going to be 450.
This is not 450. 450 is the slope.
Okay, okay.
This is 450, like this.
Okay. Okay, but we know V, right?
We know what?
V is 28. So this can
be.
be.
We know that.
So can this be V cos 5?
If you do V cos 5, you will end up finding out the horizontal component of velocity. How is knowing the horizontal component of velocity going to help you over here? Because you have to find gravitational potential energy, right? I will tell you, you have to apply trigonometric ratios.
Yeah. So this is a right angle triangle. We need to
Yeah.
find the opposite.
Yes.
We have,
Yes.
but in this we don't have adjacent or the.
But
Oh no,
you
the
have,
slope is 450, right?
yeah, the slope is 450. You have the hypotenuse. So you
Okay.
have the hypotenuse, you have the angle. You can simply go ahead and calculate. What do you think the height is going to be?
Yeah, that's going to be fine. 39.22.
Just 1 second. That's your final answer, or you're giving me the height?
Height.
Okay. Give me the final answer. MGH, do that, and then tell me what your final answer is.
Miss, can you do root 2GH?
Sorry,
Can you do
under root 2GH. Why
Yeah.
will you do that? You don't have the formulas for velocity. You don't need to calculate the velocity. You need to calculate the energy, gravitational energy. That's it.
Okay, so that's right. So
Under root 2GH will be done when you have to calculate velocity. You don't have to calculate velocity.
It's okay, Miss, I'll have to convert to standard form. 1 minute. Miss, is it 30? Is it 31 and then 1, 2, 3, 4? 3.1 into 10 to the power 4?
It should be 10 to the power 5, not 4. Hold on. You're going to go ahead and you're going to do MGH, right?
So mass.
Your height is going to be 450 sine 5. So when I'm getting that, I'm doing that, I'm getting 39.2. I will multiply that by 9.81 and I'll multiply that by 800. Multiply by 9.81, multiply by 800. So I am getting 307,799, and I can, if I convert this into standard form, this will become 1, 2, 3, 4, 5, 3.07 into 10 raised to power 5.
What if there is like for example there was 9 and there was 2 here, then how would you convert it?
I would still, first thing that you would do is you would first move your decimal. So your decimal will start moving from over here. You will move it till here.
That's when you're rounding. For example, you need to round this
No,
first, right? And then
for first you turn it into standard form and then you can round it. So you can round it to 3.1. You won't start rounding from here. You'll first turn it into standard form and then you can round it if you want.
Okay.
So generally in our exam, in the physics exam, even in the maths exam, we generally round it off to either 2 significant figures or 3 significant figures, right? So if you're rounding this off to 3 significant figures, then you would start rounding it off from here. Okay, if you're rounding it off to 2 significant figures, so if I'm rounding this off to 3 significant figures, then I'm going to make this 3.08. If I'm rounding this up to 2 significant figure, I will round it off to 3.1. So if you're rounding it off from here, from all the way over here, that's going to be 1, 2, 3, 4, 5, 6 significant figures. So generally we do 2 significant figures or 3 significant figures. So you'll either look at this number or this number. That's it. Okay, are you getting the answer?
Yeah.
Okay, all right. So that is it. We are, I think, done with this question. Use your answer in 1 to determine the useful output power of the car. Useful output power, and you have to use all the answers given to you in part 1. You can use acceleration, kinetic energy, gravitational potential energy, whatever you want, and you have to determine useful power output.
Okay. Miss, it is going to be 9756.
No,
No,
no. What formula are you using?
I'm using power is equal to energy by time. So
You're right.
first,
The formula you're using is correct. What will be the energy?
half mv square.
Just half mv square. You are gaining both kinetic energy and gravitational potential energy.
So you'll
You're
add.
gaining both of them. Yes, you will add them.
Okay, 1 second. Let's start. Okay. This is going to be 19334.
Sorry, can you say it again?
19334.1.
19334. Yeah. Strong that of the standard form?
Okay, then that's just going to be 19. Okay, 1.9 to the power 1.
Yeah. 1.9 to the power of 4. Good job. That is correct. Okay. Okay. This is a question that is related to your turning effect of moment. And then they have related it to your output power as well. So let's go ahead and take a look. Two forces, each of magnitude F, form a couple acting on the edge of the disk of radius R as shown. The disk is made to complete n revolutions about an axis through its center, normal to the plane of the disk. Write down an expression for the distance moved by a point on the circumference of the disk. So if there is a point on the circumference of the disk, what will be the distance moved by the point? Just give an expression.
2 pi r n.
2 pi r n. Good job. You'll multiply it by the number of revolutions.
Yeah.
Work done by one of the two forces. So if I ask you to calculate the work done, what would you do?
Force into this distance, which is 2 pi r n, right?
Good job. Force into 2 pi r n. Using your answer to A, show that work done by a couple produce a torque when it turns through n revolutions is given by W is equals to 2 pi n t. So using these formulas, you basically have to go ahead and show that work done is equals to 2 pi n t. So this is where, practicing your derivations is very good because it like gives you the idea that if they give you, so they often do this. You'll see questions where they will give you like 2-3 equations or 2 equations, they'll make you figure them out in part 1. And then in part 2, they will say, oh, now show that this is equal to this. So you have to use the 2 equations to get your derivation. So give this a try. You have your equation, you got your work done is equals to force into 2 pi n r. That is fine. Now you have to use that concept of work done to actually show that work done is equals to 2 pi n t. So give this a try and see if you are getting this equation or not. Do you know the formula of torque? What is the formula of torque?
Force into distance, yeah, the same thing.
Force into your distance.
Yes.
So yeah, it is going to be force into distance, right? Force and into your distance between them.
Now, can I annotate my thing and can you tell me if it's right?
Yeah, if you want to, you can go ahead and annotate. It's up to you.
Okay, Miss, I replaced work done by, Miss, is this for overall? It's for both. So that's going to be F into 2 pi r into 2 because it says of both, yeah?
Yeah, for both of them. Yeah, the total work done. Because they're saying work done by a couple. So you have to take a look at both of them.
This is equal equal to 2 pi n, and for torque, I'm taking F into 2R.
Okay, your formula for torque is correct. Uh, uh, you are getting 2 pi n, right? And then you are writing down F is equals to 2R instead of what?
Instead of T torque.
Okay.
Okay,
You have to, no, you have to start from here and then you have to show how you're getting T. You can't include T from the start. You have to give a logic for why you're writing down T in your equation. Remember, that is why I always say, since, like in the previous derivation, the one we did in theory, I said, oh, since F is equals to ma, so instead of writing down A, I can write down force upon mass. So what you're saying is correct, but you have to give a reasoning for why you're writing that T down. You can't just bring a T out of the blue.
okay, so this here we'll start by multiplying this with this here. So that's going to be, okay, so here, so it's going to be force into 2 pi r n times 2, so 2F times 4 pi r n. Okay, and then we can um Miss, what do I do after this?
Look, I'll tell you, you are on the right track. You're thinking along the right track. Let me actually explain to you how you actually are going to write it down. Okay, so you're going to write it down by saying total work done is equals to 2 multiplied by 2 pi r n. Okay, then you're going to go ahead and you're going to, so the way you word it is very important. You're going to write down this is equal to total work done. So I'm writing down TW meaning total work done. Then you can write down since torque is equals to 2 Fr. Oh, I'm sorry, I forgot to write down. It is force into 2 pi Rn, right? So you can go ahead and you can write down, when you're writing it down, the way you write down is very important. You write down since torque is equals to 2Fr, so 2Fr in the equation can be replaced by torque. That is how you're getting the T from, right? You are doing substitution equation over here. You are substituting. Since torque is equals to 2Fr, so 2Fr can be substituted for torque. That makes our equation work done is equals to 2 multiply by, so 2Fr can be substituted for torque, T by N.
Okay.
And that is how you're getting your entire formula. Okay, so what you were thinking of was the right thing, that you do have to include torque in it, and torque is equals to 2Fr. But in this particular situation, you have to say, since torque is equals to 2Fr, so 2Fr can be substituted for T. You have to give a justification for why you're including T in the equation. Where are you getting the T from? So you have to tell them, I'm substituting. I am getting it from another formula and I'm substituting it over here. I'm replacing 2Fr with T. So that is how you're going to get your equation. Now they're saying the car engine produces a torque of 470 Newton meters at 200-2400 revolutions per minute. Calculate the output power of the engine.
Okay. Miss, do we use the same formula from above?
You can use the same formula from above.
Okay.
And your own knowledge as well.
Okay. Power. Miss, will we basically do will we do this? Will we do the same thing? Work done is equal
Yes.
hour is equal
What
to
is,
work done
yep,
over time,
good
and
job, correct.
then we can apply it in the formula. Then we
Yes, so you can do work done is equals to 2
times pi.
pi n t, and then you can divide it by the time.
Yeah, and this what do we say?
Yeah,
This p and this n.
t,
Can we just use this because they gave us torque?
yes, exactly. So the capital T is going to be the torque,
And
exactly.
n is number of revolutions, which is 2,400.
Yes, good job.
And time, do we do divided 60 into 60?
Yes, by 60 seconds, exactly.
5 into 470. This time is 60 times 60, yeah, because minute into seconds.
Time is just 60. Why will you do 60 into 60? Just 60. 1 minute has 60 seconds in it. That's it.
Okay, so is it 32.81?
Hold on. No, you're doing something wrong in your calculations. You will do 2. You are going to go ahead and do 2 pi 470 multiplied by 2400, and you will divide the answer simply by 60. So 2 multiplied by pi multiplied by 470 multiplied by 2400, and then if I divide it by 60,
Yeah, it's 118,123.
yeah, 1 point, so you can round it off to 1.2, and then it's going to come 10 raised to power 5. So that is what the answer is going to be.
Okay, yes.
Okay, all right. Got it? Any confusion?
No, no, no.
Okay.